Right, hi. Session 13. So we've done chapters 1 to 4 now. I'm actually going to move on to chapter 8 from the textbook. Firstly, because it's such a great topic and I think we need to look at something really cool. And also because the other chapters are going to tie in quite nicely with some of your GCSE lessons later on. So this is a bit of a standalone topic. It's really, really fun. It's calculus. Some of you may have even heard the word calculus and think it's really scary. It's not. It's all about really finding gradients or finding areas. But for the further maths course, GCSE, it's just finding gradients. So here we go. Let's get cracking with it. Right. Okay. So calculus really is two forms really: differentiation and integration. But we're going to look at differentiation. Okay, differentiation, which is essentially finding the gradient. Okay, finding the gradient on a curve. Okay, and this is it's got so many real life applications that you'll see later on in the chapter. But for this session, we're just going to introduce it. And also, how we actually find the gradient of a certain point. So let's go straight in with an example. Now, if I had find the gradient of the curve y equals x squared at x equals 3. Okay, that could be a question. So we need to find the gradient at the point x equals 3 on the curve y equals x squared. So let's just have a look at what the curve actually looks like. Now, y equals x squared is a parabola going through 0, 0. Okay. And it's obviously a curve, but I want to find out when x is 3, if I put a point there, what is the gradient at a specific point? Okay. Now, what I would do usually, well, GCSE, I could draw a tangent on there. Oops, sorry. There's my axes again. So I could draw a tangent on there and then draw a nice big triangle and do the rise over the run. Okay, I could draw that out and I could get the gradient. Now the problem with that is it's not going to be very accurate. Okay, especially if it was a more complicated curve. So I need technique. There's a technique I can use using algebra that's going to get that very, very accurate. Now, if I zoom in on this area here, let's zoom right in. So it's still a bit of a curve, and that's my first point. So I'm zooming in. That is the point x equals 3. And what I'm going to say is I'm going to zoom in very, very tiny, and the next point, okay, the next point along, I'm just going to call that 3 plus h. Now, h is going to be very, very small. If it's a very, very small amount, as this becomes really, really small, this line here, or the tangent, the gradient at that point, will basically be the same as the curve, as long as h is very, very tiny. Okay? So, I need to know the height of this triangle and the width. Now, the height is what, okay, if I go back up here, when x is equal to 3, and this is y, well, y is equal to, because it's y equals x squared, it's just 3 squared. And if my next point, which was somewhere up there, it was 3 plus h, my y coordinate there is going to be 3 plus h squared. It's just whatever the x value is squared. So my first point here, 3 squared, and my second point, 3 plus h squared. Okay. Now, if I draw a triangle here, again, rise over run. So the gradient is equal to the rise over the run. Now, the rise is the change in the y. So it's going to be 3 plus h squared minus 3 squared. And the run is the difference between 3 plus h minus 3. Okay, this distance here is effectively going to be h, you'll see that in a minute, and that distance there is the rise, which is this coordinate minus that coordinate. Right, let's just simplify and see what we get. So the gradient is going to be 3 plus h 3 all over, this just becomes h. Now if I again expand this bracket, I get 9 minus 3h, no, plus 3h, plus another 3h, plus an h squared, minus 9, 3 squared, all over h. You'll see that a few things cancel out now. The 9's cancel, and I end up with 6h plus h squared over h. I can factorise the top. 6 plus h all over h, and the h's can cancel, so I get the gradient is equal to 6 plus h. Now remember what I said earlier, I want h to be very, very tiny. I want this to be small as possible. So I want h to get very, 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 very close to 0. I want it to tend to 0. This arrow means tends to 0. And as h tends to 0, the gradient tends to, well, just 6 plus 0. So the gradient tends to 6. And therefore, actually, because it's basically 0, the gradient is going to equal 6. Okay? Now, I could have done that, and you might even want to try and sketch this curve out, draw a tangent at x equals 3, and hopefully you'll get a gradient that's about 6. It should be exactly 6, but when you sketch, you should work out that it is 6. Now, that seems quite a long-winded process, and we'll see a quick way in a minute, but I want to show what happens in general. So the gradient at any point. So let's stick with y equals x squared. So again, got the curve y equals x squared. And this time I'm going to look at a point, just a general point, x. And the next point along, x plus h. Now, because this is y equals x squared, the height of that point is x squared, and the height of that point is x plus h squared. Okay, so the gradient, again, is going to be rise over run. Now my rise, difference in coordinates, x plus h squared minus x squared over the difference in the x coordinates, okay, which equals, if I expand that, I get x squared plus 2hx plus h squared minus the x squared over h. Now the x squareds cancel quite nicely. I can then factorise the top. And the h's cancel. And I get a gradient that's equal to 2x plus h. And as h tends to 0, the gradient will equal to x. Now that is really, really useful because at any point now I could tell you what the gradient is. So at x equals 3, the gradient is equal to 2 times 3, which was 6, which we worked out earlier, but I could also do at x equals a half. The gradient would be 2 times a half, which is 1, and so on. I could get the gradient at any point on that curve, which is quite a powerful tool. Okay. Now I could do, well, let's just look at the notation before I show you the quick way of doing these, because you might think, well, that's quite a long-winded process for some curves, and it would be. So let's look at the notation. Again, we're going to start with, so if y equals x squared, the gradient, well, we worked out what the gradient was, wasn't it? The gradient is equal to 2x. Now, more commonly, the gradient we call dy dx. So this just means the same as the gradient. Okay. You might also get the words. So it could mean the rate of change of y with respect to x. That also just means the gradient, effectively, and that in this case would be 2x. Okay. Now you might also, this is notation sort of 1. Now a second different style of notation, you could be something like this: fx equals x squared. Effectively means the same thing as y equals x squared, but we're just talking about it as a function. And the gradient, okay, the gradient, well, we know the gradient is 2x, but more commonly we call that f dash x is the same as the gradient. These mean the same thing. So dy dx, the rate of change, so this one, and this one all mean the gradient. Okay, and these two here, these are the most common. So dy dx you use when you've got y. In fact, I'll just change the color there. And if you see f of x, you must use f dash x, and those two are the most common pairings. Okay, so that's the notation you need to know. Now, there is luckily, so maybe just pause the video at this point and just write those. That's a really important notes to have in your book there. So just make a note of that. Now, there is a quick way, luckily, of finding out the gradients. So when y is equal to something times x to the power of something, these two are just constants, there is a fast way of working out. There is a fast way of calculating dy dx, okay? Now, the best thing to do is look at an example. So EG1, if y equals x squared, dy dx equals 2x. We've worked that one out above. EG2, if y equals 3x squared. Now, you could try this using the technique above. That's what we call differentiation from first principles. But you will find that the differential, if you do that, what you do is you times the power by any number in front. So in this case 6, and you reduce the power by 1. So 2 minus 1. So the actual answer is going to be 6x. Right, let's look at another example. So if y equals 3x to the 4, dy dx, I can go straight away. Dy dx is going to be 4 times 3, 12. X, reduce the power by 1. Okay, so in general, if y equals ax to the n, dy dx will equal a times n, goes in front, x to the n minus 1. And you can test that out for yourself. That will always hold true. It's got to be in that form though, ax to the n. And that is definitely worth writing down that box. Okay, right, let's look at some more examples, and then you're going to do some practice. So EG, we're on EG4. So differentiate, this is how the question may be worded, differentiate y equals half x to the minus 2. And b, y equals 4x cubed plus 2x plus 3. Okay, we're going to do a few more. Let me just write these down. C, over 4x squared, and fx. Okay, so 5 examples there. You may want to pause the video and have a go at some of these yourself. Okay, right, the first one. So I'm going to go straight in. The first number is that number, the power times the coefficient. It's dy dx because it's y. So that's going to be minus 1 x, and then I reduce the power by 1, minus 3, which is just going to be minus x to the minus 3. Okay, now this one here, we've got three different terms, 1, 2, 3. But what we do is we just differentiate each term individually, so it's no different. So the first one, 4 times 3 is 12x, and I reduce the power by 1, which is 2. Now, when it's just a 2x, that's like having a 1 in front there. So it's going to be 2 times 1, which is just 2x, reduce the power by 1, and I get 0 there. Now, this one here is like secretly having an x to the 0, because remember, x to the 0 is 1. So x to the 0, I do 0 times 3, which is 0 x to the minus 1. And that will equal, so 12x squared stays as it is, 2x to the 0 is just a 2, and 0x, that just becomes 0. So that's the answer there. Now, at this point, it's worth noting a few things. So if you've just got, let's just put this over here. So if you've got something like in general, a few more rules that are useful here. Actually, so I'm going to move that. So in general, so if y equals some constant times x, then dy dx will just equal that constant. Like here, when y equals 2x, it was just 2. And also, if y equals just some constant, something like 3 or something like that, then dy dx does just become 0 for that particular term. Okay, so that again is well worth copying up, that little box. So over here, sorry, the 3 just became 0 because it's a constant. That has, obviously the 3 has no effect on the gradient because it's just shifting the curve up or down. Right, now we've got one here, slightly harder one. Y equals 3/4 x to the 4. It's not in the correct form. So I need to first of all make it in the correct form. And that's the same as doing 3/4 and bringing the x squared up to make it x to the minus 2. So I need to do that step first. And now I follow the same procedure. So I do dy dx is going to equal minus 6 over 4 x, reduce the power by 1 to the minus 3, which is going to be minus 3 over 2 x to the minus 3. Okay. Right, next one here, d. Similar thing. The only thing I need to do here is multiply out the brackets first. So I need to multiply out the brackets. At this stage, it's still y. So it's y. That's going to be x to the 5 plus x cubed. And then I just need to differentiate each term. So this becomes, bring that down, 5x to the 4. And this one becomes 3x squared. Okay. Final one. I've got it in terms of fx this time. I'm just going to simplify this first. So I'm going to take out x squared because x squared is common in both. And also on the bottom. And what's useful here is I can just divide through by x squared. So I've got fx is equal to x cubed plus x. And then I'm going to differentiate it. So it's f dash x. And that's going to be 3x squared. And x is just like having a 1x. That just becomes plus 1. Okay, and that would be my answer. Right, all of those could be exam questions. We're going to look at one more example of a sort of exam style question that you might get. And then you're going to do some practice. So let's look at exam practice. Okay, exam practice style questions. You might get something like this. So fx equals 5x squared minus 5 over x squared plus 2. Find the gradient at the point 1, 2. Okay, so that's the question. This is probably worth quite a lot of marks actually, maybe 3, maybe even 4 marks here. So I've got fx equals that. Now my first step always is to get them all in the right form. So step 1, get each term in form ax to the n. Okay, so that's sort of step 1. So the first, what I mean by that is the first term is in the correct form, 5x squared. The second one is not. I'm going to bring the x squared up, and that becomes 5x to the minus 2. And I'm just going to leave the 2 as it is. So that's my first step, and I'd probably pick up a mark there. At this stage, I've probably picked up 1 mark. Right, I'm then going to differentiate. So step 2, because I want to find out the gradient, I need to get the differential. So I need to differentiate. So if I differentiate fx, it becomes f dash x. You must get the notation right. If it was y, it would be dy dx. And I go through each function in turn. So 5x squared becomes 10x, because the power just gets reduced. 10x, that's fine. The next one, I do minus 2 times minus 5. So that becomes plus 10x to the minus 3. And the 2 just disappears because it's a constant, it just goes. Now I'm going to rewrite this because this could be a non-calculator paper as 10x plus 10 over x cubed. That means the same thing, okay? So that is my gradient function. I've probably picked up another 2 marks here. So I've got 1 mark for that. I've picked up another 2 marks at this point. So I'm probably on 3 marks. Now, the question says find the gradient at the point 1, 2. So at the point 1, 2, well, f dash x is the gradient, and I don't need to look at the y coordinate, I just need to look at, okay, well, x is 1. So when x is 1, what is the gradient of this function? So it's 10 times 1 minus 10, plus 10, sorry, over 1 cubed, which is going to equal 10 plus 10, so the gradient will be 20, and that is the mark. I'll get an extra mark there, so that's my final mark, which would bring it to 4 marks in total. Now I could, if I wanted to, quickly look on Desmos here and just check if my answer is accurate. So let's have a look at what was the original curve. It was y equals fx squared 5 squared minus 5 over x squared, 5 over plus 2. Right, there's my curve, and it was at the point 1, 2. At 1, 2 there, well, you can see that if that is going to be, that's quite a steep gradient there, and that will be, in fact, I'm confident that's going to be 20. If you were to draw a big triangle on there, you would get 20 as an answer, so that's a good test. Right, okay, that's an introduction into differentiation. We're going to be doing more on that over the next few sessions. But for now, I want you to do a bit of practice after you've copied the notes. Page 215, exercise 8A. Questions 1 to 6, just the first and the last part on each question. For each question. Okay, and questions 7 and 8, the whole thing. And then I want you to do exercise 8B, which is on page 216. And I just want you to do questions 5 to 8 inclusive, okay? So that is session 13. Tune in for session 14 as we continue down the calculus journey. Okay? Thanks, guys. Speak to you soon.